Let's talk about some applications of what we've learned and prepare for a test on this material. So if you're watching this independently, this is just good prep and good overall summary of what we've learned. Otherwise, if you are in my class preparing for a test, this will help you prepare for the test. All right, so let's summarize. We know our first principles here. This is our limit definition of the derivative. So when we are asked to find something from first principles, we're using this formula. We're subbing in our actual f of x value and so on, and determining our limit for our function. But we've seen that we can take a little shortcut with some functions. So if I want to find the derivative of an exponential function, I take ln of the base value here times the original function. If I'm looking specifically at the exponential function with the base of e, ln e times e to the x, ln e is the function and its inverse, so they cancel out. We just have a 1 left, times e to the x just gives us e to the x. We've worked with the trigonometric functions, and we've seen that the derivative of sine x is just equal to cosine x, and the derivative of cosine x is equal to negative sine x. So those are going to be helpful, and we can just kind of use those as tools in our toolbox now instead of having to use first principles to recalculate every time. We can also extend and learn something new right away that's related. If we have the derivative of e to the x with some value k in front of it, it still is just equal to k times e to the x. So this function, any multiple where k is some constant number of our exponential function based on Euler's number, so e to the power of x is still that constant k times e to the x for the derivative. So same pattern to follow, and we'll just define here that k is an element of the real. So this will work for any real number. So as an example, if I want to find the derivative of 1 over 5 e to the x, that's just going to be equal to 1 over 5 e to the x. All right, that's pretty convenient. And we might see with a couple more examples here that it doesn't matter what our k value is. If it's 2, if it's 100, this is still going to hold true. Similarly, we have 4 times 2 to the power of x equals 4 times 2 to the power of x times ln 2. Same idea. So we're still, if we ignored the 4, just like we had before, if I want to find the derivative of 2 to the x, that's 2 to the x times ln 2, or ln 2 times 2 to the x, my original function. But now my k value, whatever constant that is, just stays in the mix as well. And it doesn't matter what that value is, whether it's 4 or 100, the 100 appears, my original function appears, ln of my base appears. So we're not going to explain why that's the case. If you want to investigate that, you're welcome to do so. This is just a brief extension, building on what we've already learned about exponential functions and adding a little extra flavor and extending that tool just a little bit further. Oops. All right, there we go. Now let's go ahead and work through some practice problems. Example 1. Find the equation of the line that is tangent to the curve y equals 2 times e to the x at x equals ln 3. So we're trying to find the equation of a line. And I know that when I want to find the equation of a line, I'm going to need a point. And I'm going to need slope. So let's think about how we're going to find these for this kind of function. Well, I'm told my value for x. Actually, let's work here. So I'm going to work on my point first. So I'm going to need some x, some y value. Specifically, I'm given my value for x. It's ln 3. And I know how to calculate y. It's given here. So my y value is going to be 2e to the power of x, where my x is ln 3. And well, we know that e to the power of x and ln of whatever our inverses are going to cancel out. So I can rewrite this as ln 3 and 2 times 3, or finally as ln 3, which is just some number we can evaluate to find its approximate value, and 6. And I guess we might as well do that right away. It's good to have exact values, but if we're going to be graphing this on our line or on a graph, it's like, well, I don't know what value ln 3 has. How do I find that? We just kind of eyeball it and then label it exactly. So that's going to be approximately 1.099, comma 6. And I guess technically we found this earlier already in our previous video, or we can just quickly find it now with our calculator. Next up, we need our slope. We know our original function, y equals 2 e to the x. We know that the function that gives us the slope of our original function is the derivative. So I want to find the derivative. So y prime. And hey, we already know this is a special function. The slope or the derivative function is just going to be the same as the original function. So it's going to be 2e to the x. So if we're trying to find the tangent line at this specific point, let's evaluate, let's plug it in. So that's fine. So what's the slope when x is equal to ln 3? Well, let's plug it in. My y prime, my slope is 2e to the ln 3. Hey, we've already done this calculation. Y prime is just going to be equal to 6, and we get that from over here. Exact same thing. And that's my slope. All right, I have slope and a point. Let's find the equation of our tangent line. So we have y, I'll switch my color here. Y minus y1 equals m. X minus x1. So this is our slope point form for my linear equation. I know my point, so let's plug in our values. Y minus y1, which is 6, equals my m value, which is 6. X minus, and x1 is my value right here. So I can approximate it with 1.099, but it's good to be exact. So I'm just going to write in ln 3 here, because remember, we defined our x value here as being exactly ln 3. So let's make a conclusion and make sure we've actually answered our question. Therefore, the equation of the tangent line is y minus 6 equals 6 times x minus ln 3. Or I can rewrite it as y equals 6x minus 6 ln 3 plus 6. And I could combine these terms and get an approximate value just to put it into y equals mx plus b form. But we want it to be exact, so I'm going to leave the ln 3 in there to represent that exact value. Now let's check to see if our results make sense. And in order to do so, we're going to use Desmos. So theoretically, under this purple square is an image of a Desmos image. I can't show that to you given the format I'm using to make these videos. So we're just going to switch and take a look at Desmos in a separate window. Well, let's take a look at Desmos. I've gone ahead and put our values in for us. So we have, we have our function that we were looking at, y equals 2e to the x. I've also graphed the inverse function just so we can have that for flavor and get a feel for what's going on and what that looks like. We've looked at our point of interest, ln 3, 6. That was the exact value, and then it's shown here on our graph, and it's found our approximate value here of ln 3 is equal to approximately to 1.099. And then we've graphed our proposed answer. We hope that this is the tangent to our 2e to the x curve at the point ln 3, 6, and it looks good. We can see that it touches the graph right at that point. We can see that that looks like the tangent that we expect. It has a positive value. Everything looks good, and we can zoom in a little bit, but honestly, it's not going to look much different as we get close. Just our lines get closer and closer together. So our answer visually looks correct. So obviously that doesn't prove that it's correct, but it's additional evidence that we have done this correctly. So that looks pretty good. Next up, let's take a look at a word problem that's going to involve exponential functions. A biologist is studying the increase in the population of a particular insect in a provincial park. The population triples every week. Assume the population continues to increase at this rate. Initially, there are 100 insects. We are asked to A, determine the number of insects present after 4 weeks, and B, how fast is the number of insects increasing when they are initially discovered and at the end of the 4 weeks. So let's identify our components here. When I have an exponential function, and presumably you've learned about these before in your other classes, generally it's going to look like this: y equals a times b to the x, where a is my initial or starting value, b is 1 plus my growth rate, or if it's decay, 1 minus decay rate, and x is our variable. All right, so let's identify these components from my word problem. So I have a few different numbers here. Let's take a look at them one piece at a time. So we need an equation or a formula. So we're trying to find our function. And we're finding population, so I'm going to call this P, and it changes based on time. So P as a function of T is going to be equal to a b to the power of T. A is our initial amount. So how many insects did we start with? Well, or what was our initial population when time is equal to 0? So initially, that means at the beginning, T equals 0, there are 100 insects. So that's going to be my A value. So A is equal to 100. B is 1 plus my growth rate, or in other words, it's what number are we multiplying by each time we go through one of our periods, each time our exponent increases by 1. And it tells us that our population triples each week. So triples means times 3. So that's going to give us our B value. So our B value is going to be 3. And then T is just a variable, but let's mention that T is time in weeks. So this is the period during which our growth occurs, so every week. All right, so we have found our function, and let's just make sure we define our variables. So we're going to have let P be the number or size of the population of insects as a function of time, where T is time measured in weeks. All right, cool. So now that we have our equation, we can actually use it. So A asks us to determine the number of insects present after 4 weeks. So in other words, what is P when T is equal to 4? So 4 is our input into our function. What is my output? So let's just plug that into our equation. Equals 100 times 3 to the power of 4. 3 to the power of 4 is 81, so 100 times 81. And please be careful with your order of operations. This is a 12U course. I assume you know how to do this. Whoops. But just to confirm. But please make sure you aren't doing 100 times 3 and then to the power of 4, because that's going to give you a really huge number. So don't do that. Just watch your order of operations, please. Exponent applies first, so 4 to the power of 4 applied to 3, so 3 to the power of 4 gives us our 81, then multiply by the 100. So we're going to get P of 4 is equal to 8100. And it's a word problem, so we should have a concluding statement. So we'll say, therefore, after 4 weeks, there were 8,100 insects. All right, I'm going to resize this and move this off to the side so we have room to answer B. Make sure you've had a chance to look and read through this before I make it tiny. All right, with that moved out of the way, let's switch colors and let's try B. So B asks, how fast is the number of insects increasing? So what's our key word here? We want to know how fast is something happening. In other words, they want to know the rate at a specific point in time. So maybe that's the instantaneous rate of change. How do we find that? Well, we're going to use our good friend calculus. And specifically, we're going to use the tool called the derivative. So I want to find the derivative of my exponential function in order to find the instantaneous rate of change at a given point. So my original function that I just found, p of t is equal to 100 times 3 to the power of t. What did we just learn about finding the derivative of exponential functions? Well, if we're multiplied by some constant k, that's still going to be there hanging out. My base and my exponential value or my exponential variable are going to be there. And I just need to multiply by the ln of my base. My base is 3, so we're just going to multiply by ln 3. And this function represents how fast they're increasing. So this is how fast they are increasing. And now let's actually do something with this. So the first time it asks us to work with is when they're initially discovered. What do we know about the conditions at that point? Well, if they've just been discovered, no time has passed yet, and so time is equal to 0. So we're going to find this when t equals 0. So we're going to find p prime of 0 equals 100 times 3 to the power of 0, which of course equals 1, times ln 3. That's going to equal 100 times 1 times ln 3. So our exact value is going to be 100 times ln 3. Of course, that doesn't really have a lot of meaning to us, so we'll also list the approximate value just so we can mentally get a feel for what this value is. And it's going to be 109.86, so we'll round. So it's approximately equal to 110 insects per week. So remember, this is a rate. So it's not just a number. It's not what is the number of insects. It's the rate of change. And we want to answer this, so we want to give a whole number in our word problem, because just giving an exact value doesn't really help us understand what's happening here. So let's make a concluding statement. Therefore, initially, they are increasing at 110 insects per week. So please remember, we're finding a rate of change. A rate means we're comparing two quantities, something over something. So I need to say specifically that this is insects per week. Or in another question, it might be dollars per hour or liters per minute or whatever. It's whatever we're measuring on our y value, on our y-axis, which in this case is number of insects, over whatever we're measuring on our x-axis, which in this case is time measured in weeks. So remember, this is just like finding slope. Change in y over change in x, change in number of insects over change in number of weeks, or insects per week. So please remember that when you're writing these questions out. That's how you're going to find and state your units of measurement. Our second question, I'll switch my color again here. Asked for at the end of 4 weeks. So t is going to be equal to 4. And then we're going to repeat this. So p prime of 4 is 100 times 3 to the power of 4 times ln 3. So we're going to have 100 times 81 times ln 3. So my exact value is going to be 8100 times ln 3. And that's good for a calculated answer, but in terms of understanding what's happening here and stating our conclusion, we're going to round. So if I evaluate that on my calculator, 8100 times ln 3 is going to give me a value of 8898.7. So we'll round up to 8899 insects per week. So therefore, at the end of 4 weeks, they are increasing at a rate of about 8,899 insects per week. And why does that change so much? Well, remember that we're dealing with exponential functions here. It's not a linear function where it increases by the same number of insects every week. It's increasing by the same tripling rate every week. So as this goes on, my graph would look something like this. It's going to get steeper and steeper. So my slope here and my slope here are not going to be the same. As time goes on, that rate is going to increase more and more. And you're like, well, how does that happen with populations? That's crazy. Wouldn't you get like extremely, extremely high growth? Yes, you would. But in real life situations where we're dealing with animal populations or the population of any living thing, there's going to be limiting factors. You're going to run out of space to actually have that many insects. You're going to run out of resources like food. You're going to have other things like predators eating the insects, bad weather, whatever else impacting that growth. So the exponential growth is not truly sustainable. Sometimes people tell you, it's like, oh, well, you know, you can make so much money for every person that joins your group. And, you know, if you tell 3 people and they tell 3 people and they tell 3 people, well, that's just exponential growth. You'll be making crazy money, or the population will be growing crazy. Or if you just tell one person about this story and they tell 2 other people, or you tell 3 people and they tell 3 people, the whole world could know in under a week. It's like, yes, in a perfect exponential situation, but exponential growth is just a model for what could happen in an ideal situation. It doesn't take into consideration real world effects like death, like the animals dying or running out of food or things like that. So it's still a very useful model to understand what's happening here, but it's a tool that we have to use with some care when we try to use it to convince somebody of something.